Parallelism. It's a fun word to say. uh, what exactly is parallelism? Well, if you ask me, I think the simplest explanation would be just doing a bunch of stuff at the same time. So, and there's many ways that you can do stuff at the same time. There's SIMD, or single instruction, multiple data. So that would be having a single instruction set run in parallel over many threads working on different data. There is multiple instruction, single data. So using the same data, perform different actions on it over multiple threads or multiple cores. And then there's the most, probably the most powerful version, multiple instruction, multiple data. That's just doing everything. Different data worked on by different instruction sets, etc. Yeah. If you, for an example of a single instruction, multiple data set, multiple data, you might think of, say, taking a bunch of arrays and performing, say, an aggregation on them, instead of in one core running the aggregation for one array, then the next array, then the next array. You could assign these arrays to independent processes that do that will do those arrays. So, like, say there's 5 processes, you essentially divide the time by 5, theoretically. It's not that simple in practice. So in general, parallelism has been the shift that processing has taken, especially in the modern age. This is because CPUs at this point can't really get that much faster. We've hit a wall where we cannot make the transistors smaller because then they leak, and we cannot add more transistors because, and we cannot increase the clock speed that much because it'll overheat. And heating is one of the, cooling is one of the biggest problems with high transistor counts and clock speed computers. So if you can manage to parallelize code, chances are it will be much faster. Let's look at one of the most extreme cases of parallelism in the GPU. So what problem does this solve, right? If you look at a standard computer monitor, you probably have a 1920 by 1080 screen. That's over 2 million pixels being refreshed 60 times a second, right? Those are crazy numbers. And CPUs are doing quite a lot. They have so much more to do than change the color of pixels on your screen. And this is where an architecture that's better suited to this in the GPU comes in. So if you look at a comparison of the number of cores on a CPU, and I would argue that this is quite an extreme CPU in itself. Typically, you would find 2 or 4 cores in a standard CPU. The GPU will have hundreds, if not thousands, of cores on one single processing unit. Yeah. This in itself allows the GPU to do many more calculations per clock cycle than a CPU. So, all right, it'll have hundreds or thousands of inexpensive cores, and the work will be divided among the cores, and they work they work in lockstep to render images. So in one clock tick, you will probably perform thousands of calculations on a single GPU instead of one calculation on a CPU, right? So you can imagine for pixels where where there are thousands of individual colors that need to be calculated, how the GPU just like speeds that up. Another thing with that makes the GPU powerful is that essentially for each pixel, the same instruction set is being run. So the calculations of how light interacts with objects you're rendering, the normals and stuff like that, everything is just the same calculation for each one. So this would be an example of a single instruction, multiple data set architecture, and GPUs just really take that to the extreme. But chances are we're not writing shaders on a daily basis. So where can we find use in, where can we find parallelism in our day-to-day, right? So if, say you might find processes that are being run and they don't really depend on anything else, but they're heavily used. You might consider parallelizing those processes. And also, we should also take note of where it is, even implicitly. So if I think of services like AWS, these sort of are able to scale because of parallelism, because they can take a process and replicate it over a bunch of nodes so that stuff essentially can be run at the same time. So finding parallelism and also taking account of where it is implicitly can be a really powerful skill in boosting the productivity of the things we develop. But there are some difficulties. So first up is finding parallelism can be quite difficult. It's not a trivial task. It's not a trivial task. And it also requires a very different mindset to sequential programming, where we might think of starting at one point and ending up at the end of the process. You need to account for many different factors like the cache, cache hits and misses and so forth. Then there's synchronization. So if your processes either like require data or need to modify data from at the same memory location or around the same, even around the same memory location can be a problem. You need to really think about like how to coordinate that. And just because you can do it in parallel doesn't necessarily mean, well, sorry, introducing parallel can make it really hard to test your program and make sure that it's correct. And there's also the issue of overhead. So when you're starting a system up, it can be really expensive to start computationally. So some considerations before you try to shove parallelism into everything you do. You need to ask yourself, do you need it? If you only have like a really like a small process, sometimes the overhead of introducing parallelism can just make that worse. So yeah, you also need to consider where the bottleneck in your performance is. Does it lie in computation or is it in memory? Trying to parallelize stuff that's memory bound can be quite taxing because the CPU will not be the limiting factor. It will be how many accesses you need, say database calls, etc., and update when you're updating and so forth. So parallelism is the best in certain situations. Do not try cram it in everything. It'll blow up in your face. Okay, thank you.